Changes in chemical reactions is what we're going to talk about today. When you have a chemical reaction, usually one of two things is going to happen. You're either going to need to put some energy into the chemical reaction for it to take place. So in some cases, like for example, photosynthesis. Photosynthesis requires energy, right? Where does the energy come from in photosynthesis? You biology people. The sun, yeah. So you need energy from the sun, right, to make that reaction happen. Okay, so in some cases we need to put energy into the system and into the chemical reaction for it to take place. In other cases, when you burn things, especially, let's burn it. Yeah, burn it. When you burn stuff like fuel, for example, like we just filled up the car with gas today. When you fill up with, when you burn that fuel, you get energy out of the system, right? You get energy as a product. It produces energy, right? So depending on the reaction types, and by the way, those are called endothermic and exothermic reactions, determines if you need to put energy into the system or you get energy out of the system, okay? And that's what we're going to look at today. And we're going to look at basically 3 different ways of writing those equations today, all right? And once again, this is always good diploma question, guaranteed 1 or 2 questions probably on the diploma, something to do about this, okay? Heat is absorbed or released by chemicals as they react. Energy is involved whenever chemical bonds are broken and new bonds are formed. So there's always energy that's being, whether it's required to form or to break bonds, there's always energy involved there, okay? Chemical bonds are sources of potential stored energy. So there's always potential in a chemical bond, okay? There's always stored energy in there, all right? If you break a bond, okay, breaking a bond absorbs energy. That's what we would refer to as endothermic, okay? Breaking a bond requires energy, takes energy in, okay? While creating a bond is going to release the energy, okay? That's exothermic there. Endothermic reactions, the system's potential energy increases. So I want you to keep in mind this right here. This, of course, refers to potential energy here. So how much potential does it have? Okay? How much energy potentially does it have? Endothermic reactions, potential energy always increases. Okay? There's a couple ways of looking at this. Basically, the energy absorbed, so the energy that's taken in, is always more than what's released, okay? There's a lot more energy in the beginning part, basically how much is absorbed, than there is released. The energy in the bond breaking, okay, breaking bonds, is a lot more than the energy that's created with the bond making part at the end, okay? And like I said, we have different ways of representing these systems here, okay? So make sure you know that the potential energy increases in an endothermic reaction. In an exothermic reaction, the potential energy always decreases, once again here, okay? Potential energy decreases. If you think about that, endothermic versus exothermic, obviously it's the opposite for exothermic, but think about that. If you put a lot of energy into the system, if the energy has a lot of energy built into the system, then it has the potential to release the energy, right? So if there's a lot of energy involved in the first part, okay, if you have a endothermic reaction, you have a lot of energy stored up in that particular compound or whatever the case might be, or that potential reaction. When it's released, that potential energy goes down, okay? Well, what releases energy? Exothermic. When you burn fuels, right, you're basically giving off energy. Well, does it have energy left to stored up now? No, you're burning it off. You're giving it off. So potential energy for exothermic, not so much, okay? Decreases as you go. And once again, the opposite here. We're going to look at something called enthalpy. Enthalpy is a fancy word basically to just talk about that specifically. How much energy is either gained or lost in these reactions. Enthalpy is a fancy word for basically which involves really endothermic and exothermic reactions. It's the heat that's involved with that. In joules, for example, in kilojoules, how much heat's required for this reaction to take place, how much heat is given off if this reaction takes place. That's what enthalpy is, okay? When a reaction takes place, enthalpy change, also known as delta H, is equal to the heat absorbed or released by the system, okay? The delta H of a chemical reaction is equal to the change in the potential energy of the reactants and the products. So basically it's going to look at the reactant side and say how much energy is stored up in there, or how much energy do I have on the reactant side, how much energy do I get as the products, okay? And in fact, we're going to do something called Hess's law later on, and that's exactly what we're going to do. We're going to compare the reactants and the products to each other and see how much heat is actually given off by these chemical equations, okay? And we're not there yet, of course, but we're eventually going to do that, all right? Enthalpy changes may be expressed as the following, okay? The enthalpy of a reaction is usually measured in what we call kilojoules, of course, okay? So that's an entire reaction. And then there's something else called molar enthalpy, and that's in kilojoules per mole. And we'll talk about the difference between those, and the best thing to do is give you some examples of those two things. It's a little bit, for right now, it's a little bit different way of writing the same thing, basically, okay? Molar enthalpy is the change in enthalpy when 1 mole of a substance undergoes a process. We're going to look at that today here, okay? Molar enthalpies are associated with all types of processes. And you may see some little subscripts that go with these, okay? And there's quite a few here, but these are kind of the main ones we're going to use. If you see a little delta RH, once again, delta H is the enthalpy change, okay? Delta RH stands for the molar enthalpy of the reaction. So for the molar enthalpy for that particular reaction to take place. Delta FH, F stands for the formation, okay? So you'll see that, delta FH, molar enthalpy of the formation. Delta CH, okay, would be a term that we would use for combustion. Another one that you may see occasionally is delta DH, which would be molar enthalpy of decomposition. Okay. So you could use that one as well. Now, you know, if you get these wrong, is it a big deal? And the answer is no. If you say delta RH, you know, I mean, we should know it's a reaction, we should know it's formation, we should know it's combustion, we should know it's decomposition. Sure, yes. But in the big scheme of things, does it matter? When are you going to see this? You're going to see this on the diploma. It's going to say calculate the delta FH, or the delta FH of this compound is this, or something along that line, okay? So basically that's what they're going to be telling you. Or the delta CH for this particular reaction is this, okay? So they're going to tell you probably these things anyway, okay? But we should use, preferably we should use the right notation there, okay? In an endothermic reaction, okay, endothermic chemical reactions always have a positive enthalpy change. Make sure you know that. So they're always positive, right? When we think back to yesterday's questions, okay, when we talked about which ones were positive, they're the ones that we had to put energy into, right? If we're going to heat up water from 20 degrees Celsius to 80 degrees Celsius, how are we going to do that? Well, we need to put energy into it, right? That would be an endothermic reaction. We are putting energy into that system to heat up from 20 to 80. That's a positive enthalpy change, okay? That is an endothermic process right there. We're putting energy into it, okay? So in this case, of course, and once again, the potential energy, of course, is increasing because it's endothermic, okay? Balanced chemical equation for photosynthesis, okay? Now, it's actually on the next slide here for you anyway, and that's fine. But A balanced chemical equation for photosynthesis looks like this here. Okay, 6 carbon dioxide, 6 waters, gives you glucose here and some oxygen. Okay, so here's the balanced chemical equation here. A couple things to take a note here. This is what you guys would have done in Chem 20, yes? True? Okay. The only thing we're doing now is we're going to do the exact same stuff, guys. We're going to do reaction types, etc., but you're going to associate the heat or the energy that's involved with this equation. Okay? That's the only thing we're adding on here. So sometimes people start freaking out here and they're like, oh my god, this is so confusing. It's not. Okay? It is the same stuff we did before, same reactions, except now we have this heat involved, or this energy that's required. And you'll look at this when it says here, the enthalpy change of the reaction is written as a positive 2,802.5 kilojoules. So what does that mean? Well, it means that for this reaction to take place, do I have to put energy into the system, or am I getting energy out of it? What is it? You're putting it in, right? And in fact, turns out I have to put in 2,802.5 kilojoules of energy for this reaction to take place, this specific reaction to take place. Okay? If I'm putting this energy in to this system, okay, where do you think I should put 2,802.5 kilojoules? On the left side, on the reactant side? Think about this. If I have to put this energy in, do I put it on the left side, or do I put it on the right side, the product side? What do you think? Left side, the reactant side, right? If I'm going to put energy into it, where do I put it? I put it on the left side, right? True? Make sense? Well, guess what? You already know one of the 3 ways of writing the equation then. If you simply put this into this side here, that's one of the 3 ways that we represent this equation. Okay? You're 1/3 of the way there. Okay? So, let's take a look at how the different ways are. There's 3 different ways of writing these equations, and that's all we're doing today. We're going to look at the 3 different ways of writing these equations. Okay? The first one's called delta H notation. And they're going to tell you on the unit test, on the diploma, which one of these represents delta H notation. Okay? And you just have to simply pick the right one. That's all it is. Okay? Now, there's a few little things involved, but basically that's about it. The balanced chemical equation with the delta H as a term following the equation. So we would write out the balanced chemical equation, okay, this part here, which are already done for you, unfortunately. Like I said, I wish this wasn't done for you today. You write out the balanced chemical equation just like you would have done in Chem 20. And at the end here, you're going to put delta H is a positive 2802.5 kilojoules. That's called delta H notation. What that tells you is that this equation here needs a heat, is an endothermic reaction, first of all, because it's a positive, right? Endothermic. First of all, endothermic. And it requires 2,802.5 kilojoules for this reaction to take place. Okay? So that's the first way you would write this system. Okay? And once you get to your questions, you'll kind of see what we're talking about here. But I would ask you, what's the balanced chemical equation for photosynthesis? You would write it out. The heat associated with this equation is so-and-so. Write it as delta H notation. Write it as the next one. Write it as the next one. Okay? So the first way is delta H notation. Okay? You just simply put the heat at the end. Positive for endothermic. Obviously negative for exothermic. We'll give you an example of that too. This is the second way. As a enthalpy change as the reactant, so inside the equation. So we've simply, like you said, we would put the 2802.5 on the reactant side. This tells you once again that this is endothermic. Okay? Because it's on the reactant side. So, okay? Tells you it's endothermic. Right? It's on the reactant side. So you could put that term in, you could put that heat into the equation here. So 6 carbon dioxide, 6 waters, And this much energy, 2802.5, would give you glucose and oxygen. Okay? And finally, the last one, so that's 2. The third one is what we call potential energy diagram. And a potential energy diagram looks something like this here. On the side here, okay, we would put the potential energy in kilojoules. Okay. Now, all endothermic reactions will look like this. They start out lower, okay? For this one here, let's see. I think we're just going to go up and over, okay? So, you're going to label this diagram accordingly as well. So we're going to take basically our reactants here, okay? 6 carbon dioxides, 6 waters. We're going to write out the reactants down here. So this is my reactants here. 6 CO2 gases, 6 waters. Okay. Balanced chemical equation has to go here, so it has to be balanced. So 1 and 2 usually are, good things to do before you do this. We're going to put here delta H. In other words, in this case, our change in our heat, or basically our delta H value, has to be a positive. We're going to put that energy into it. Okay. And what was it? A 2802.5 kilojoules. Okay. And then we're going to get our products. So if we take this, and we put in our energy, we will get our products as the result here. Which is the C6H12. It's O6, isn't it? And 6 oxygens. Is that right? Is that balanced? 12, 18. Sure. And that'll be the products as a result. The only couple things important here, guys, is, well, first of all, we have to make sure that this is balanced. Okay, so balanced, this number has to match up with your delta H, your overall delta H, and those there. Okay, once again, balanced. Okay, so that's what a potential energy diagram looks like. Okay, and you'll see that once again. That'll probably be one of your diploma type questions or one of your Unit 1 test questions. All right. Those are the 3 ways of representing endothermic reactions. They're exactly the same for exothermic, just the diagram is going to be a wee bit different, and where you put a few things, of course. Exothermic reactions, like I said, once again, always have a negative enthalpy change. Okay, heat's always given off in this case. Okay, it's produced. Heat is produced. All right. The potential energy of the system is decreasing. That makes sense. Think back to the diagram here for a second. Look at this. Potential energy is going up here. Potential energy is going up here, yes? So it's increasing. Look how much energy we have now. Look at all the potential we have to do work up there compared to down here. Potential energy increasing, right? Yep. Yeah. Sure. Okay. Potential energy for this one, exothermic, is decreasing. Okay, and I'll show you the diagram for that. You're going to see that we're losing energy. Because why? Because we're giving it off. It's being produced, right? We're letting it go. So exothermic, always negative enthalpy change. Okay. Balanced chemical equation for the combustion of ethanol. All right. Well, it's right here for you guys once again. Balanced chemical equation for the ethanol here is C2H5OH. 3 oxygens, 2 carbon dioxides, and 3 waters. And I'm going to give you guys some practice on Monday with different types of reactions again here. So we're going to go over that on Monday. And if you need a little bit of help with that today, we'll do that. But I think the ones today are they're okay, I think. I don't think you'll be too bad for the homework today. And I can help you out with those a little bit. The enthalpy change associated with this particular reaction is a negative 1,234.8 kilojoules. So that would be your product, of course. Hey, if we're getting this out of this system here, where should I put this 123.48 kilojoules? Should I put it on the left side or the right side if it's going to be a product, if I'm giving it up? Probably on the right side, right? So that's once again, that's one of the ways we're going to write it. That's number 2 option, right? So how are you going to write this? Once again, what we call delta H notation. Delta H notation is always delta H at the end. And it's the only difference here, guys, is balanced chemical equation, very important. And then the delta H here, the negative means exothermic, of course. Okay? That tells you that this reaction is producing energy, it's giving it off, it's releasing it, okay, et cetera, et cetera. It also tells you that the potential energy of this particular reaction is decreasing. Okay, potential energy is decreasing. All right? Second way, as a part of the product, okay? But remember, one of the most important things with this one is, once again, balanced chemical equation, yeah, it's all good here, guys. Don't forget, this is being released. We need to put a plus there, okay? So we do need to make sure that we put a plus 1234.8, right? It's kind of like, you know, we get this, we're getting this, and we're getting this here, right? We're not going to put a negative there, because if we put a negative there, well, technically, how would you solve for that if you're thinking in strictly math? Well, first of all, we don't write negatives in chemical equations. Never have, never will. Okay, that we never subtracted stuff in a chemical equation. We always put plus, right? If we did put a minus here, well, technically it would be a plus over here, wouldn't it be? If that was the equal sign, right? That doesn't make sense, because then it would be endothermic. So we need to make sure we have a plus sign. Energy term always appears as an absolute value. It's always a positive, okay? So if it's endothermic, it goes on the left side. If it's exothermic, it goes on the right side as a positive, of course. We're getting that energy out, okay? And finally, another potential energy diagram, okay? Now, we don't need to worry about specific numbers here. Will they give you some specific numbers? They might, sure. Okay, we'll worry about that later. Generally, what does this chart look like? What do all exothermic ones look like? Well, they all look pretty much like this, okay? Okay, right here, what was it, ethanol? So C2H5OH. I think that's a liquid if I'm not mistaken. And oxygen. Okay, we need to balance it. I'm going to be lazy here. Yeah, 3. Okay. On the other side here, we're going to get our products, which of course would be CO2 gas here and water gas. Okay. And let's see here. 2 and 3, I guess, eh? 2, 3. Make sure, okay, one of the biggest mistakes that I always see with these, I don't think this is overly tough as far as writing these out. One of the biggest mistakes is I don't see that balance. You just write the reactants, the products. Okay, you have to have it balanced. And in this case here, we're going to start here. We're going down to here. Delta H in this case is a negative, whatever it was. What was it? 123.48 kilojoules. Okay. So we are losing that much potential energy when we do this. Okay, we're giving it off. So once again, it's decreasing. All right. So that's what a potential energy diagram would look like for that. Once again, you will include the negative here because we're talking about strictly the delta H notation. Delta H is negative 123.4. You would put, if you're going to put that in the equation, we do need to change it to a positive, of course. Okay, that's it for you guys. All right. Like I said, I'm just going to pause here for a sec. Let's go back to here for a sec. What you have to, one of the biggest things we have to keep in mind here is that, just look up here, guys. Don't worry about that. You got a whole weekend for homework. Trust me. You got nothing else going on. You have no friends. Okay, so it's fine. All right. This particular reaction, right? I mean, it's obviously going to be different for each one. Okay, we'll show you how to figure those out and all that other stuff. So just be patient. But for this particular reaction, right, if I burn this, I get this, I need that much energy. Or let's even go back to this one here. Maybe this one's going to be even easier. For this particular reaction here, this balanced chemical equation, this is how much energy is given off. Okay? What would happen, okay, because this is actually one of your homework questions, so I kind of want you to think about this. Well, that's fine. What if I burned 2 moles of this? So let's say I had 2 moles of that and I burned that. Well, first of all, it's not balanced anymore, right? Do you agree with that? Okay, so you would say, well, I would need 6 moles of oxygen, right? I would need 4 moles of this and 6 moles of that, right? True? Because it's still balanced now, right? I just doubled everything. But let's say I actually burn 2 moles of that. Do I still get 1,234.8 kilojoules of energy produced? How much do I get now? Twice as much. Sure. So now I would get twice as much energy produced, right? Because you're burning twice the amount of fuel, right? So you should get twice the energy. If I burned half of this fuel, I should get half the energy, right? That's actually called molar enthalpy, which is what we're going to talk about, not actually Monday, but Tuesday. All right, but this kind of ties into one of your questions here. They talk about how much it is for 1 mole of something, but then when you balance it, it turns out the only way to balance it properly is that you actually need 2 or 3 in front of that value there. So if you balance this, and it turns out that you have to have 4 in front of this fuel here, but they tell you the energy for 1 mole of this particular fuel, well, then your delta H, don't forget, has to be times 4 as well, right? Because all this stuff goes together, okay? So the only thing different from Chem 20 is we're still doing the same thing. This is in a specific ratio, yes, and so is this. This is part of this equation. We have to make sure we have that there, okay? And that's what this whole unit's about, how much energy is being produced, how much energy is taken in, et cetera, okay? That's thermo, that's the heat part, dynamics, yes? Okay? So think about that. I'll tell you what right now, I believe it's question 3. Think about that when you're doing that question, okay, when you balance it. Decomposition, how do you guys, the first, number 1's given to you. Decomposition, guys, I'm not going to give you that one because I want you to do that on your own. You got to remember a couple things, okay? First of all, when we talk about first things first, when we write equations, right? We need to think about, what are these called again? Do you remember? Somebody knows, hey? Whoever took Chem 20 last semester? Come on, people. What are these ones called again? Yep. Yeah, and you didn't cheat. It wasn't even one of them. Molecular elements. You have to know your molecular elements. Molecular elements are very handy for formation and decomposition, right? Which I believe, if I'm not mistaken, is, well, only number 2, I guess. Okay? So, remember how you remember these? I have no brighter, clever friends, people stupid. Yes? Now you remember? Okay? There's only 5 people in here that don't remember that because they weren't in my class. Otherwise, everybody remembers that, right? Everybody, it's given, right? I have no brighter, clever friends, people stupid. So if you have those, you need to use those, right? I have no bright or clever friends, people stupid. Right? And those are the molecular elements. Remember, they're more stable like that. That's why they come like that. And the second thing is, so for example, if we're doing, let's say, I'll just give you this one, magnesium phosphate here. Let's do decomposition, okay? Don't forget when you're doing decomposition, each element by itself, okay? So, magnesium, phosphorus, and oxygen, right? And if you need a little help with that, like I said, Monday we're going to do this again here. We're going to go over some of these, and I'm going to include the enthalpy change for you. It's going to be a little bit of practice for you. Balancing wise, don't forget you're going to have to put a 2 here. So that's 4 phosphoruses. I'm going to do this fairly quickly because we're running out of time. 8 and 2 is 16, so that's an 8 there. Okay, that would be your balanced chemical equation. Now, they might tell you the delta H for 1 mole of magnesium phosphate. That's fine, but this balanced equation is for 2 moles. So you need to keep that in mind. That's kind of what we talked about earlier there, right? And real quick here, so that'd be an example of something like number 2 for you, okay? Similar to that. Number 3 here is a combustion. So remember, for combustion, right? If you have in your fuel, if you have carbon, you get carbon dioxide gas, right? So if carbon's in the fuel, you get carbon dioxide produced, yes? If you have H here, you get H2O gas produced, okay? There's another 3 actually, but I don't think, I'm going to tell you right now, in Chem 30, these 2 are the main ones here, okay? We almost solely just focus on these. The other one, of course, is S, gives you SO2. By the way, if you have oxygen in the fuel here, what happens if you have oxygen in here? What do you get over here? What do you get? Just wait, we're not done. What do you get for oxygen there? Do you get anything over there? No, it's just extra oxygen, right? So you don't have to write, there's no other product over here for oxygen. It's just another, it just adds more oxygen to the fuel, basically, okay? So that's all right? Let's have those questions done for Monday, obviously, please.